Hello dear viewers. So we're gonna have a discussion about the fundamentals of AI. I hope you enjoy my presentation. So I want to first talk about the origins, evolutions, and the current trends of AI. So the quest to create machines with human intelligence dates back centuries from Leonardo da Vinci's humanoid bird sketches in 1485 all the way to Alan Turing's 1950 paper that proposed the possibilities of machines that can exhibit true intelligence, setting the stage for the field of AI. So the key AI concepts and applications on will be rigorous and strong AI, where weak AI focuses on creating machines that can do specific tasks, while strong AI imagines with machines with general intelligence, and also thinking versus acting, where thinking AI tries to mimic human intelligence, while acting AI focuses on the actual on actions and behaviors done by the artificial intelligence. So now, the evolution of uh, AI, AI techniques. So now AI started with rule-based expert systems and has advanced advanced towards a machine learning models. Its predictive capabilities are phenomenal. Versatility in modern AI lies in using data insights and therefore real-time analysis, making it indispensable in healthcare, finance, and other sectors. So now, AI's impact on problem solving. AI addresses complex issues by identifying the problem, analyzing the tasks, and choosing the best techniques to solve that problem. It employs knowledge representation, state-space search, and rational thought to tackle real-world challenges across various fields. So throughout the entire discussion, I always be referring to my AI project that basically uses an artificial intelligence to create a restaurant rating system. So now this team focuses not only on air quality but also on health safety. So by sensing data such as carbon dioxide levels, user feedback, and all this information needs to generate air quality scores and health safety ratings for each restaurant that's registered in the system. So now it just calculates it can create real-time data such as the temperature, humidity, also user feedback. User feedback is about the air quality and ventilation of restaurants, and all of this is used to improve the AI models over time. So the system defines the problem space by looking at issues like unhealthy air quality, overcrowding, and then it uses machine learning to predict health safety scores based on sensory data, weather, and user feedback. AI techniques such as natural language processing, analysis of reviews like Staffy or Fresh to improve air quality predictions. So the system continually updates its prediction and enhances its accuracy as new data comes in. It learns from past feedback and sensory sensor readings to improve better ratings over time. Problem solving in state space search. So problem solving in AI often uses a state space search approach to create an effective system for solving a problem. So what you basically we need is to define the problem precisely, analyze the problem, isolate and represent task knowledge, choose the best problem solving technique. So formal description of the problem. So a state space is a set of all possible states reachable from the initial state by applying a sequence of operators. So the initial state is the starting point of the problem space, while the goal is the desired outcome or solution. And the operators are the actions that move from one state to another. So there are basically two types of search techniques. We have informed search and uninformed search. Where informed search, no extra information is used beyond the problem description, while informed search uses heuristics and domain-specific knowledge to make the search process more effective. So in the previous slide, we talked about uninformed search and also informed search. And uninformed search is also known as blind search. That one where no information other than the problem description is provided, and examples could be breadth first search and depth first search. And then also we have informed search, which is also known as heuristic search, where some information about the domain is used to head in the general direction of the goal node, and it uses heuristics, which is a function that estimates how close a state is to the goal. So the heuristic function takes a state and returns an estimate of its distance from the goal state. So a standard approach of creating heuristics is problem relaxation, which is basically you get the constraints and you relax them, make it easier to create a heuristic function. And heuristic is admissible if it underestimates the cost of reaching a goal node from any node. So the only thing required for a heuristic to be admissible is that it never returns a value greater than the actual cost path. So informed search strategies, another being graph search. This search strategy that explores the problem space with aid of heuristics to focus on promising areas. And there are also local search algorithms on being hill climbing, which moves towards the goal by selecting the most promising state. Through it can get stuck, in local maxima. Then we have best first search, which balances the advantages of depth first search and breadth first search by using heuristics to guide the exploration. So application of problem solving in AI. Data mining. The classification of problems can be framed as a state space search in which the initial state, like sensor and crowdsourced data, is classified into a goal state which can be either good, bad, or moderate using operators such as prediction rules, types of intelligence. Problems are formalized into rules, constraints, and outcomes that can be added to mathematical computations, and this corresponds to logical mathematical intelligence. The same problem arises: can an AI determine which factors such as traffic, humidity, or visa are more important in predicting air quality? This question challenges the design of a heuristic approach. Project example. The objective of a project is to predict a restaurant's air quality score, which is a classic state space search problem. We define the problem as initial state, raw unprocessed data, e.g. carbon dioxide, crowd, and location data. The goal state, which is a definitive classification of the air quality score ranging from 0 to 100, and the actions which applying our machine learning model to transform the initial state into the goal state. Problem solving by search. Now we're going to talk about and or graphs. And or graphs represent the solution of problems that can be solved by decomposing them into a smaller set of problems, and all which must be solved. So heuristic search, a OR-star algorithm. OR-star algorithm uses heuristic search procedures to optimize the search process in and or graphs. The heuristic helps to guide research towards promising solutions by estimating the cost of the value. So game playing, board games and game trees. Now games like chess and checkers can be modeled using game trees, and a game tree is a layered tree presenting the possible choices players and alternating at each level. So the strategy is determining the optimal moves by analyzing game trees, maximizing chances of success while minimizing opponent's advantages. So there's minimax and alpha beta pruning. So minimax algorithms helps extract the best first move in a game tree, focusing on minimizing the possible loss while maximizing gains of the max player. The alpha beta pruning, an optimization technique to minimize the computation effort by eliminating branches of the game tree that won't affect the final decision. Application or problem-solving research. Data mining. If states with similarities are grouped together, then it's referred to as clustering, and this reduces the search space since the system can focus on one state from the cluster. Types of intelligence. Navigating the game trees, which has several intricate branches, enables the system to visualize all possibilities to find an optimal path. This demonstrates spatial intelligence. The system simulates all possible futures, helping you to anticipate any outcomes before acting. This is similar to the simulation argument. Project example. In a restaurant air quality data, the initial state of the restaurant reports condition and the goal state is a safe dining badge. Using search-based reasoning, our system optimizes paths if traffic plus crowding is going to equal to risk and suggests alternatives. If reviews equals to mixed or sensors are missing AI, such as predicted outcomes. Similar to alpha beta pruning in game and games heuristic pruning, prune irrelevant factors, focus only on the most impactful data for faster, reliable health safety scoring. Knowledge representation and reasoning. Knowledge representation basics. Knowledge representation and reasoning. This is concerned with how the agent uses what it knows in deciding what to do. Intelligent behavior. How agents make decisions based on what they know. And symbol system hypothesis. This proposes that intelligent behavior arises from manipulating symbolic representation. 2. Requirements for knowledge representation. Knowledge requirements. The knowledge representation language must allow effective computation and accurate reasoning. Knowledge representation language features should support logical and implementation levels of representation. 3. Preposition logic. Now, preposition and well-formed formulas. Now, prepositions are declarative statements that are true or false. Well-formed formulas are syntactically correct formulas. De Morgan's law describes how logical operations like negations interact with conjunctions and disjunctions. Symbolic versus connections AI. Now, symbolic AI uses discrete symbols and formal logic for knowledge representation, while connectionist AI relies on neural networks and connections to represent and reason about knowledge. Application of knowledge representation and reasoning. Data mining. Association with e.g. frequent patterns in sensory data like high carbon dioxide with overcrowding can be transformed into first-order logic expressions, e.g. for x, if that x has high levels of carbon dioxide and is overcrowded, then it implies it's poorly ventilated. So this provides a structured way for AI to reason. This transformation allows raw data to become actionable knowledge. Type of intelligence. So the linguistic intelligence concerns itself with creating a formal language with a precise syntax and semantics to clearly express complex concepts and relationships, while intrapersonal intelligence leads to meta-reasoning. Our system can reason about its own knowledge, e.g., assessing certainty of diagnosis or identifying what critical information is missing. So, knowledge representation reasoning raises the question: can all knowledge be captured symbolically? In our project, users impressions such as stuffy or fresh carry nuisance that may resist full formalization, reminding us of the limits of rigid logic. Project example: in our restaurant air data, knowledge representation encodes rules like for all locations, if the location has high traffic and poor weather, then it implies that it does risky air quality. Using logical preposition logic for badges: if safe, if it's not smoky and it has low particles smaller than 2.5 millimeters. And first order logic for predictions. Reasoning integrates crowdsourced data with external factors, enabling actionable insights like avoiding roadside eaters during dusty season for scalable health decisions. First-order logic. Knowledge formalization in first-order logic. Declarative knowledge. Knowledge is represented as sentences that can be proven true or false. Conceptualization. A process that formalizes knowledge by defining universal discourse, functional basics, and relational basis. So, certifiability. A key notion of truth where sentences are true in a given representation of a model. Quantification. Universal quantification. A sentence that is true for all variable assignments. By extension quantification. A sentence is true for some variable assignments. Syntax of first-order logic. Syntax describes the structure and formation of valid logic expressions in the first-order logic. Terminology of quantifiers. It describes how negation interacts with quantifiers. Interpretation and model. Interpretation is a way of assigning meaning to formula. Model. An interpretation that satisfies a logical formula, making it true in that context. Axioms and inference. Axioms are foundational truths, while inferences are made using rules that derive theorems from axioms. Inference in first-order logic. An inference involves deriving conclusion from premises using first-order logic. Rules of inference uses formulas to derive theorems and proofs from axioms. Resolution and refutation. Resolution, a rule of inference, is used to prove unsatisfiability in a set of clauses. Resolution refutation demonstrates unsatisfiability, proves logical implication. Soundness. Any conclusion derived through resolution is valid, while completeness. Resolution can derive any conclusion that is logically implied. Answer extraction. Query answering. First-order logic queries can be answered by extracting models that satisfy the query. Answer extraction process involves finding the most general unifier and resolving it with existing clauses. Procedure controlling of reasoning. Infinite resolution. Resolution can be held in an infinite branching, requiring control strategies like closed elimination. Application of inference in first-order logic. Determining. Classification identifies statistical patterns and outputs labels facts, and first-order logic provides machinery-driven reasoning. We can transform these outputs in a knowledge base of logical predicates and use inference rules to derive new, non-explicit knowledge, turning correlation into actionable and reasonable conclusions. The entire process of constructing proofs from axioms with first-order logic is a implementation of logical mathematical intelligence. The AI system manipulates symbols according to strict logical rules to arrive at guaranteed conclusions mirroring a fundamental human cognitive ability. The Chinese room versus human versus real understanding. This raises a question aligned with the Chinese room argument. A system can correctly manipulate symbols to infer diagnosis, but does it actually understand medical concepts, or is it just merely shifting syntax? Now, project example, in our AI restaurant air quality data, sensors grapple with noisy crowds and reports require reasoning and uncertainty. So fact 1 of carbon dioxide being greater than 1000 ppm and PM 2.5 being greater than 35 micrograms per cubic meter. If both are high, then the air quality safety is risky. By combining symbols and progressive reasoning, the system derives expandable yet uncertain where recommendations ensure users get trustworthy guidance even with incomplete data. Reasoning and uncertainty and planning. Reasoning and uncertainty. Uncertainty arises when agents lack complete knowledge about the environment, and the probability theory helps reason about these uncertainties. Bayesian's networks model conditional dependencies between variables using the Markovic property of effective reasoning. The Bayes rule updates beliefs with new evidence. Decision networks combine probability and utility to create decision making and uncertainty. Valid information is to access the wealth of additional data. Planning. Planning agents create actions to achieve goals using situation calculus to present world challenges. The STRIPS representation formalizes actions with preconditions and effects. Now, goal-struck planning breaks complex goals into sub-goals. Through it can be incomplete, leading to Sussman's analogy, action conflicts. Planning helps identify mutual exclusive actions, and graph planning uses graphs to search for valid actions. Planning and decision making and machine learning. Planning and decision making. Real-world planning domains are complex and often do not satisfy assumptions of basic planning methods like strips or partial order planning. Heuristic decomposition breaks a problem into smaller manageable tasks. Conditional effects specify how actions have different effects based on the real-world state. Sequential decision problems involve decisions where actions depend on previous outcomes modeled with the Markov decision processes. Pearman equation computes the optimal policy MDPs, ensuring the best sequence of action is chosen. Partial observable MDPs deal with the situation where not all the state information is visible, requiring dynamic belief. Networks to model uncertainty. Machine learning. Machine learning is a subset of artificial intelligence focuses on algorithms that learn from data and improve with experience. Classification and regression are the common types of ML tasks where classification assigns labels and regression predicts continuous variables. Supervised learning identifies patterns without label data, while dimensionality reduction reduces feature complexity. Learning decision trees use information theory to build models that classify or predict labeled data. Reinforcement learning teaches machines to stop making decisions based on rewards and penalties.